All right, now that we have derived our differential equations that represent the rate of change of liquid molar holdup as well as the mole fraction in our distillation column, we are now we're going to simulate this dynamic distillation through Python using Google Collaboratory. So for part B, we are given a bunch of values that we can use. So starting with two equilibrium stages between the condenser feed stage as well as the feed stage and reboiler, meaning that we'll have 7 total stages in our distillation column. We have a feed flows of F equals 1 moles per second, and Z is 0.5, which is the mole fraction of the more volatile component. And then we will be assuming constant relative volatility at 2, and then that liquid flows via the overflow at a rate of 12 times our holdup minus our initial holdup raised to the 1.5 power, where holdup naught is 1.2 moles for each stage. And then we have our distillate flow rate at 0.6 moles per second, as well as a reflux ratio of 1. And then lastly, once we get our distillation column set up, we are going to want to incorporate a proportional level controller with our Kc being equal to 1.5 to adjust the bottoms flow with the reboiler holdup as a control objective. And then we will simulate this time response of the compositions and holdups in the column over a period of time for 500 seconds. So moving into our Google Colab, we have imported numpy as np, which is our Python library, and then our solve IVP function, and then lastly our plotting function using plotly.subplots. So here at the top of this cell, I have included the kind of like the layout of the distillation column in which I had derived our equations for in the previous part. And then I went ahead and kind of listed out the parameters that are given in the problem. So we can go ahead and run that cell. All right, so moving into our coding here, we know that the liquid at the tops for the first and second stage is going to be equal to our reflux ratio R times the distillate flow rate. And then next, we know that our molar holdup at the top, MT, is going to be equal to our liquid levels at the top, and then that will be divided by our Francis-Weir constant. And then this value will be raised to the 2/3 power, and that is from our Francis-Weir equation. And then lastly, for this line, we are going to be adding our initial molar holdup, M naught. All right, so now that we got the top set up, we now want to set up our bottom. So LB is going to be our liquid at the bottom, is going to be equal to the liquid at the top plus Q, which is the liquid fraction of our feed, and then that will be times our F, which is our feed flow rate, and then similarly with our molar holdup at the top, it's going to be, I'm just going to tab this line in, replacing the same thing except for instead of the liquid flow at the top, it's going to be the liquid flow at the bottom. All right, so now that we have defined our liquid at the top and bottom as well as the molar holdups, we now want to define an equation for our vapor at the top and we can define this as our liquid flow at the top plus our distillate flow rate. So we can define our vapor flow at the bottom, and we know that this is going to be equal to our vapor flow from the top minus 1 minus Q, and this is going to be the value of the vapor subtracting from the Q, which is the liquid fraction of the feed, and then that will be again times our feed flow rate. Alright, so now that we have defined conditions for the liquid and vapor at the top and bottom, as well as the molar holdups, we will now want to define some initial conditions for our liquid. We now want to define some initial conditions for our liquid. So we can define that xi for our initial conditions is going to be equal to an array of values of up to 7, which is going to be our n. So we want to go np full, and then we want it to have the shape like our number of stages, and then we want to fill the value of the initial mole fraction of our feed, and we define that as z. And then we want to define our initial molar holdup in our stages, and this is going to be equal to to reference our problem. The condenser and reboiler also filled with feed liquid at initial holdups equal to 10 times the holdup in the rectifying and stripping section. So for our initial molar holdups, we want to use np.r underscore to concatenate this as a row, and our first value is going to be 10 times our molar holdup at the top, mt, and then for our second stage it's just going to be mt and then mt. So that's for our first 3 stages, and then for our feed stage we are going to use the molar holdup of the bottom, and then we're going to finish this off with mb, and then lastly we are going to use 10 times the molar holdup at the bottom, and that is for our reboiler. So now that we have defined all of our initial conditions, we now want to run that cell, and then we will move into defining our function, and we can name this our right hand side of our differential. Within this function we are going to depend on time, and then we're going to want to use a vector here. We can name that vec, and then lastly we want to include our reflux ratio, just in case if we want to come back to this code and kind of incorporate a way that we can evaluate different reflux ratios, and we can do that more simply instead of just going up to the top and entering in new numbers. If we want to run this function over and over again, we can just use this r and run it that way. So here we want to unpack our vector, which we had included in our function above, and we want to do that with our x and m, and we are going to want to split this using our np.split function, and we're splitting this vector into 2. So after unpacking our vector, we want to include our relative volatility equation, which is going to be y is equal to x times alpha, and then that is divided by 1 minus x plus x times alpha. So that is our relative volatility expression. And then we want to define our change in our molar holdup, and we're going to want to define our dm as an array of zeros. So we want to do mp dot zeros I'm going to use like M. So next we want to define the change in our molar fraction, and that is going to be equal to NP dot zeros, and this one will be like X for our molar fraction. And then next within this function, we're going to want to define our vapor, value error, our vapor, and it's going to be equal to another array of zeros, and this will be like M. And then lastly, our liquid is going to be equal to np.zeros like M as well. And these are just kind of defining initial points for all of these variables, creating a list more like an array, and it's filling them with zeros. That way when we run this function over several iterations, it will start at the initial steady state and then add on to the points afterwards. So next we want to go ahead and hard code in our first index value for our liquid. First number of our liquid is going to be equal to our reflux ratio times the distillate flow rate, and that is for the condenser. And then we're going to want to redefine our vapor at the top, and this is going to be equal to um, first number of our liquid, which is going to be our reflux ratio times the distillate, plus our distillate flow rate. And then next, our vapor at the bottoms is going to be equal to the same as was up here. So we're going to come down here and paste that in. So next we are going to want to go ahead and update our array of our vapor compositions. So this is going to be equal to this concatenated list and the 0 to the top. This is going to be for the next 3, so I can go ahead and do some shorthand. And then similarly, I'm going to have the vapor of the bottoms, and that is going to be multiplied by 3 for our bottom 3 stages. Next, we want to update our liquid composition, and we want to update our second value in our index all the way until the very end. And this is going to be equal to our Francis Weir constant, and then this will be multiplied by our molar holdup times our molar holdup, and this will be similarly from 1 to -1, again stating that it's going to be the second value in our array all the way until the very end. And then this will be subtracting our initial molar holdup, and then this will be raised to the 1.5. Piece of this puzzle that we're going to add is going to be our proportional controller, which is going to be controlling our bottom flow rate at the reboiler. So we want to go ahead and define our Kc, which is our controller gain, and this is going to be equal to the value of 1.5. And our new B we can define as our B underscore Kc, showing that it's controlled, and this is going to be equal to our original B plus our Kc, our controller, and then going to be multiplied by the first value in the array of our molar holdup, So we want to have -1. And then this is going to be subtracting 10 times our initial molar holdup, M0. I'm going to check that I have that equation correct. So we have the controlled B is going to be equal to our original B plus our Kc times the reboiler holdup minus 12 moles. And the 12 moles comes from 10 times our M naught. And our M naught is 1.2, so that is correct. So next we want to go ahead and define which scenario we would want to use this controlled B. So we want to use an if statement. So we say if our new controlled B is going to be greater than 0, we will want our last value for our liquid, which is going to be in the reboiler. So we want -1. This is going to be equal to our new controlled B, B underscore Kc. So then next we want to define our else statement. So if our controlled B is going to be less than 0, we want L -1 for the last value. We want this to be equal to 0, saying that there is no liquid in our reboiler. So let's exit that else statement. All right, so the next step, we are going to want to define our change in the molar holdup from the second value in our all the way until the very end. So 1 to -1, and this is going to be equal to the vapor that is in the um, the third stage all the way until the end, and that is going to be subtracting the vapor from 1 to -1, and then we will be adding the liquid that is going to be that is coming out, and we will pull from the second to last. So we do -2, and then lastly we're going to be subtracting the liquid that is at the 1 to -1. So this is basically our derived expression that we derived on the whiteboard, translated into Google Colab, and using syntax for the array in order to simultaneously calculate the change in the moles at um, at each equilibrium stage in our distillation column. So continuing the change in our molar holdup in our third stage, which is going to be our feed, is going to be we're going to use a little shortcut plus equal, saying dm3 is equal to itself plus the feed. So next, our initial change in our moles at our condenser is going to be equal to our vapor at our stage below, and then this is going to be minus our distillate flow rate, as well as subtracting our reflux ratio times our distillate, and that value is the liquid from our condenser, and the value of the change in our moles in the condenser is always going to be 0, because we have perfect vapor flow control, as well as neglecting the vapor dynamics. Okay, so next we want to code in our reboiler change in moles. So we want to call our last number in the array, and this is going to be equal to our liquid of our -2, and then we will be subtracting the liquid from our reboiler, the last one, as well as subtracting the vapor coming from our reboiler. So we'll again use -1. All right, so that is our 4 expressions for the change in the molar holdup. So now we need to go ahead and define our change in the mole fractions of each equilibrium tray. So doing so, we know from our derivation on the whiteboard that we will need to basically multiply each individual component in these expressions by their mole fractions at the respected stage. So I'm going to copy this, and then I'm going to come in here and paste this in, and we will need to update this to represent the um, fractional composition at each stage. And then so for our vapor, we will need to, we can start with our composition from the second stage all the way to the reboiler. So here we will multiply the vapor composition, and this will again be following the syntax. Okay. And then we're going to want to multiply this by 1 to -1. And this by the liquid. So we can do x -2, and then again 1 to negative. The next, for our feed stage, we're going to want to multiply this by z, which is the composition of our feed. And then for our condenser, we will multiply this vapor by the vapor fraction. So we'll do 1. And then for our distillate, subtracting the R times D, this is our liquid at the condenser. So we'll multiply this value by our x time at 0 index, calling for the first number in the array. And then lastly, we will multiply this by x -2, and then multiply this by x from -1, and then lastly multiply this by our y at -1. And this last line is for our reboiler. So now that we have all of this in for our function, we will now need to sort of unpack our DMX. So for our derivations, I'd use the product rule. So we'll do that similarly here by saying that dx is going to be equal to dmx minus x times dm. And then this is going to be divided by our m. And next we will want to return as a concatenated row using np.r underscore. and we will be returning our dx and our dm. Just need to make sure x and m, yep, so we want to make sure we had the same order there. Shift enter. So next we are going to want to we now want to calculate and solve using the solve IVP, so that way we can put some numbers to these values and see how our dynamic distillation runs. So we will store our result under res, and then this will be equal to our solve underscore IVP. And our function here, we are going to want to use an anonymous function. So we are going to call our lambda, and we're going to call this t. And we're going to supply a time, so we can do t vec, and then for our r here, we're going to use the reflux ratio of 1. We go for our time span, and here we go from 0 to t end, and I will still need to define our t end. However, we can keep going for this line of code. All right, so next for our initial guesses, we can go ahead and supply a concatenated row of our initial of the liquid compositions, as well as our molar or moles in each tray initially. Next, we want the method to be equal to redow, and then lastly, we want our dense output to be equal to true. Great. Oops. I need to put the t end above this. So our t end from this problem, we know that we want to run it, run the simulation over a period of 500 seconds. All right, so now that we have our IVP function, we now want to define some parameters for plotting purposes. So we will call tplot. This is going to be equal to np.linspace. And for here, we will start at 0, go until t end, and then we will support an index of 50. All right, so next we want to plug in our results from our initial value problem in order to plot them in our y-axis. So we can call this, what do you call it? We can call this final res, and this is going to be equal to res.sol. This is going to be evaluated at tplot. Okay, so next we want to plot, or not plot, we want to create values for our x's and for our m's. And these are going to be split from the array, and the array is going to be like our final res, and our sections are 2, and our axis is going to be equal to 0. So that's just the support index of our array. All right, so next we can go fig is equal to make subplots, and here we will want our rows to be equal to 1 and our columns equal to 2. We can go fig dot add scatter. Values are going to be equal to our t-plot. Our y here is going to be our x, which is the liquid composition at each stage. We will want our mode to be equal to lines so that we can visualize this plot. And then we will place this plot into the first position. And then lastly, we will give it a name. And we will give this we'll call it f, x, and then we will need to put a bracket in here. How we can put an I, and then close that off. All right. So now that we have finished this, we can go ahead and copy, Control C, and then we will want to paste this here, Control V. So for this one, we want to change our Y to the M, as well as changing the name to M. So the way that we have this set up, we are using an I in our name. So we will need to include a for I, and then this will be defining our X and our M. We will enumerate and then use our zip function. And then lastly, we will call our X's and our M's. So put the colon, and then we'll need to move these into the for loop. Next, we want to update our layout. We go fig dot update layout, and we can make our height equal to 1,000, the width equal to 600, and our template we can do Seaborn, some cool colors. All right, Shift Enter. So here are our plots. On the left, we have our liquid compositions, our X, and then on the right, we have the molar holdup. So you can see that in our condenser, we have the most liquid, and that is due to the vapor flowing upwards and condensing. And in the reboiler, we have a very small amount. And then here for the holdup, we have the greatest holdup in the condenser, and then the reboiler, and then our in-between stages are all holding pretty steady at a consistent level around 1.3 to 1.4. So this is all for part B. Thank you for watching.